outline of the talk will be as such. First, I will make the topic aware to the general audience. And then I will talk briefly about the classical mechanics and quantum mechanics, which are two ways of running simulations. And some more in-depth discussion will be on the hybrid approach, which includes both quantum mechanics and molecular mechanics. With this, we will also discuss one case example of carbonaceous material in which we will talk about graphene oxide. And we will see how the simulations are helpful in assigning the experimental spectra. So, as I said, the first topic will be on making the topic aware to the general audience. So the first thing is why basically we want the computation modeling, because in the era of instrumentation where we can get real-time validation of what is happening within our sample, what is the requirement to do the same experiments in the in silico platform? So the first reason is, first we want to create the model and we want to see the spatial location of each atoms with respect to the environment. So this is one typical example where we can see amino acids, which are the monomeric units. They combine to take polypeptide chain, and in particular a protein, where we can see different kind of structural arrangements known as secondary structures. So the later part comes the visualization. When there is more than one entity and they come together to make a macromolecular complex, it's more important to see the visualization aspect, and then we can define what are the prominent ways of interactions. So this is the second module, which solves the purpose of computational modeling. But however, these two things are more of static, which do not include the dynamic insights. So when we talk about the dynamic insights, it will be more about the statistical insights, because the atomic position is now on the probability basis. And then we describe which of them are more rigid and which of them are more flexible. In short, we'll be answering the complexity of life. All right. So if we talk in scientific term, the purpose of computation modeling is to assign experimental measurements. So in brief, it is to understand the mechanism behind the experimental outcome. Say, for example, you get something with high intensity or low intensity, you should be able to answer why is it so. Likewise, the atomistic and electronic details of interaction, which we will see, and this particular deals with the spectroscopic measurements, in particular the optical measurements. In another way, we can also quantify the peaks that we are getting, for example, the particle size or maybe the wavelength and the energy associated with any electronic transition or the interaction participating. So with these fundamental terms that we generally obtain from the experimental one, however, we do not know what are the causative factors of each individual peak or each height that we are getting. And hence, the computational modeling will not only give the aesthetic look of the system within, but it will also answer the reason behind them. All right. So now the fundamental question arises is, although the physical theory is, the responsible factor behind all these interaction phenomena, however, which one of them will be answerable? For describing the spectroscopic events. So one is the classical mechanics. Say, for example, if I give you one quick example from real life is, suppose you are looking at a leaf, you will get a green color out of it, because all the lights that is being thrown to the leaf, it will be absorbed except the green one, which will revert back and you can sense the color. So that intuition that the leaf is of green color is basically because of the classical mechanics phenomena. So this is the classical phenomena that is happening. However, if we go deep inside, where we look into the ground state and the excited state, we then realize that there will be an electronic transition, and this gives rise to some energetic differences, which in turn can be described in terms of wavelength. And this answer is obtained through the quantum mechanics. So in principle, the spectroscopic features that we used to attain from the instruments, they are more probably described by the quantum phenomena. And so we need the quantum mechanics there. However, everything which is present in a system cannot be accounted by quantum mechanics. This is the bottleneck, because the method itself is quite costly in terms of CPU investment, and hence we cannot take the full model into the consideration. However, in order to solve that, we generally undertake the system of interest, that is a small portion, including fewer atoms, in order to define the quantum mechanical phenomena within. So we will look into details in the coming slides about it. Now, So that was a very brief introduction about the computational modeling requirements. And now we will talk about the aspects how basically the computers are recognizing what we are feeding them. Because ideally computers knows nothing. It's just the algorithm that is being designed by the human itself. So it's more important first to know how we educate the computer so that the computer can give us something which is reliable and valuable. Say for instance, if you look at the screen, you can see that there are several spheres of different colors. So the only way to distinguish them is first the color, and the second, which will be in a little bit broader sense or a quick sense, is the size of them. But these are very theoretical concepts. If I assign some quantitative values to them, for example, the atomic radii, now it becomes more meaningful scientifically, because then we can assign these spheres into different elements. And so one of the way with which we can educate the computer system is the atomic radii or the van der Waals radii associated with individual elements. Now, this is one of the criteria with which we can describe the atoms in the in silico environment. What could be the another approach? So the another fundamental approach will be the charge of the system itself. So for this, we will take a look of very fundamental concept which was studied in class 12th, that is Rutherford atomic model. So where we can see the arrangement of electrons and protons and the outer shell where we have all these electrons present. And the most crucial part is the valence shell electron, because in order to satisfy the valence, we generally make the bonds. So, for example, if we look into the different element system, we see that there are different number of electrons present in the outer shell, and which will basically participate in sharing, either donating or accepting. And with this, we can see. With this, we can see basically how the bonds are being created. Say, for example, between S2O or between CO2 or between N2 atoms. So these are the electrons which is being shared, and this is how we describe to the computers that there are two elements which are in close proximity such that their electron clouds will be shared, which will be depicted in terms of bonds. Now, these are the fundamental concepts to describe individual atoms. However, the main aspect with which we will educate the computer is the partial and the formal charges, because these charges will matter when one electron comes within the periphery of another one. So when we talk about the partial charges, it is the delta kind of things, which is not really zero or not really one. For example, however, the opposite to it is the formal one, where we will have either plus or minus, say +1 or +2 or -1, so on and so forth. So one of the very simplistic way of doing this is, say, for example, we talk about NaCl. So if we dissociate it, it will become Na plus and Cl minus, which will be referred as the formal charges associated with this. However, when we talk about the amino acids, say, for example, where we have NH3 plus at one end and COOH negative at another end. So these are the partial charges which are present over the atoms. So these differences in the delta, the relative differences in the charges over the atoms actually matters when we try to simulate or when we try to bring one system in close proximity to another, where the interaction level will be described. All right. Now, these are the molecular representations with which we generally see using the visualizers. Say, for example, the PyMol, the Chimera, or the VMD software, where we see all these atoms and the constructs or overall the macromolecular arrangement. Now, few other concepts are also important in order to describe the computational modeling, that is the intermolecular forces, especially the electrostatic forces. Now, this is a typical arrangement of an atom where you can see that the electron probability is shown in the outer shell. So these are also called as the electron clouds, which will be interacting among themselves. So electronegativity is the measure how, with which the extent of, attracting something. Say, for example, in H2O molecule, O being the electronegative because it have the lone pair of electrons, which can be capable of interacting to others. So this is a typical example of H2O, where you see the electrostatic arrangement, electronegative on oxygen and electropositive on the hydrogen part. So likewise, the electron transfer is another case where the two systems can be interacted, and this is one of the example of very fundamental type. All right. So we talk about the electrostatics. The next one is the van der Waals interactions. So van der Waals will describe the hydrophobic interactions, and this is very important because although they are weak, but they sustain, basis of life. So these kind of interactions you will see in terms of dipole moment, where there will be partial positive or partial negative charges induced because of the environment. So there will be a couple of terms. Say, for example, dipole-dipole interaction, where you see the arrangement of a typical atom, but there is delta positive and delta negative on both sides, and it will be attracted to the opposite one. So another case is dipole and induced dipole, where one will be say a neutral one, but in presence of a dipole, it will be induced later. And third one be induced dipole, which is known as London dispersion or Kimura forces. So these are typical interacting types, which are important to describe the molecular phenomena. All right. So to sum up, we have say ion-ion interactions where the formal charges are important. We have ion dipole interactions. Say for example, between Na plus and water molecule, we have formal charges with partial charges. We also have dipole-dipole interactions. Say for example, HCl molecules, and we have van der Waals interactions where dipoles will be induced. So altogether, when we model a material within the computer system, these are the typical interaction types which will be governed by these charges types, and overall phenomena we then correlate or corroborate with the experimental. All right, so now we will talk about the classical mechanics, and I feel like you already have a very nice lecture in the previous session where Professor Dash Mahapatra talked about the molecular simulations or the classical mechanics. Now, as I said, the classical mechanics, the name itself suggests that it can be realized from a very superficial way, and it can also account a very large system. So when we talk about any system, the most important part is the total energy of the system. And when we deconvolute it, we get several components. For example, we get the stretching, we get the bending, torsion, and van der Waals and electrostatics. So van der Waals and electrostatics are the two which we discussed in the previous slides. Now, if further we want to classify these five interaction types, it will be of two types. One will be non-bonded, where we are talking about the interaction phenomena which are governing through space. And another one will be the bonded phenomena, where the bonding between any atoms will be the causative factor. So this is obvious because when we talk about the bond, either we will talk about the two atom system, and we will talk about the stretching of the bond. So here you can see this is the bond phenomena which can be governed by the spring factor. This is the angle phenomena, which is again taking place between three atoms. This is the dihedral phenomena, where we will be accounting four atoms, and we will be describing the relative change between the planes. So these three interaction types are bonded, and it will be governed through bonds. The later two here are the non-bonded interaction phenomena. So this is the Lennard-Jones potential, where we have repulsive and attractive forces, 12-6 terms. And this is the electrostatic phenomena, where charges of two atoms and their distance of separation accounts. So taken together, all these summative forces between the atoms, it will determine the relative stability or the position of the system and the overall flow of the trajectory. Now, why we discuss about all these forces is because we want to describe the material and its nature in a whole. So here you can see that there are several phenomena. For example, the protein binding affinity, or maybe the surface modification with which it will attract other molecules. Or maybe within the biological system, you will see that there are some helical alpha helix where the hydrogen bonding between first and fifth amino acids are important. Or you have beta sheets where parallel or anti-parallel hydrogen bonding between two sheets are important. And in absence of either them, it will be random coil. Likewise, when you have the hydrophobic surfaces exposed, they will come into aggregation. This will not only taking place in the biological system, but also in the colloidal materials. Similarly, we also have several nanomaterials onto which either the stabilizing agent or the proteins or some other molecules can be adhered. So overall, these phenomena are important because it will govern different kind of events that is taking place within the real life system. So first of all, this interaction phenomena is important because it stabilizes the system. and in which the electrostatics is one of the dominant term. The next one is hydrophobic, or we can also describe it as the van der Waals forces. However, these two interaction types we can derive from the simulations or the modeling tools. There is hydrophobicity also, which is important for the aggregation phenomena. Last but not the least, often we also want to model the system which mimic our experimental system. So in order to do so, we tune the temperature. For example, we either elevate the temperature from from the room temperature to the desirable one, or we may also take part with replica exchange, where different temperature systems can interact with each other. Similarly, the pH of the phenomena pH of the system will affect the protonation state, and we can model the titrable materials. All right, so if we get the insights from these classical treatments, sometimes we can find the rare conformation, and we can also describe about the kinetics between a different state and how fast they are exchanging among themselves. We can also talk about the secondary structure. This is in particularly important for bio-oriented materials. Then we can also talk about the electrostatics, how one macromolecule is being attracted to another one. We can also describe about the energetics of the state, where, for example, the close association, which are non-covalent in nature, can be accounted. And we can also see the diffusion property of a material, where the Brownian motion or the random collision motions can be described. Now, these are the terms in the previous slides that we discussed. Altogether, they can be accounted as the classical phenomena, because we are not going into the depth of individual atom or their probability distribution of electrons. However, it is a overall crude phenomena. But when we want to model the electronic properties, it is quite difficult to accompany with the classical system. Say, for example, when we talk about bond breaking and bond formation. So this is one example where we have SH group and a chromophore. But with the exposure of light, there will be a bond formation where the proton from this SH group will transfer to N, and S will make a covalent bond to this carbon. So this phenomena is very difficult to describe in terms of classical mechanics. So this is normally taking place in sensor-based proteins. The another phenomena is, say, for example, within our eyes, where we have rods and cones, and we can sense the darkness and the lightness. So this takes place because of isomerization at a particular point, and this is from the cis conformation to the trans conformation. Again, this little phenomena is quite valuable in real life, but it is very difficult to describe using the classical mechanics. Likewise, when we talk about the highest occupied molecular orbitals and the lowest occupied molecular orbitals, we cannot describe it using the molecular mechanics. And last but not least, when we talk about the absorbance spectra, we get several peaks in the experimental one, but the electronic transition that is responsible and the oscillatory strength, which is responsible for the height and can be correlated with the intensity of the peak, they can also be obtained using the same features. So altogether, these features describing the electronic properties cannot be described as such using the molecular mechanics, but they require quantum phenomena. Now let's see what is this quantum mechanics all about. So when we talk about the classical mechanics, it is kind of a gradient where we can roll up or roll down very easily. And so it can accommodate a large system, and using molecular dynamics, you can elucidate various properties. However, when we talk about the quantum properties, it is quite complicated, because first, no two particles can have the same quantum number. This is the very fundamental textbook code. And so the tiny elements will be confined to their individual quantum level. And hence, in order to solve them, we have to adopt the complicated Schrodinger equation. So we will again look into the physics behind the molecular mechanics and the classical mechanics phenomena. So when we talk about the molecular mechanics, we basically get the physical approximation. No matter how big the system is, we can always accompany it using the molecular mechanics, and we can elucidate some property. But then when we want the model to be highly accurate, we need to go into the quantum region. So this can also be realized using this free energy potential energy surface plot, where on one axis we have energy, on the another axis we have the reaction coordinates. So when we talk about the molecular mechanics, it will give the energetics say at this level, but relatively the quantum mechanics will be at a much lower level. So energetically this is much stable, and this relative energy gap will be accountable when we want to go into the model accuracy. All right. So now, as I said, in order to solve the quantum mechanical phenomena and understand the electronic properties, it's important that we should solve the quantum mechanics. And the quantum mechanics, as such, it looks very simple using the Schrodinger equation, but then the eigenvalues and the operators, Hamiltonian operators, and the energy one is not so trivial to solve it. And that word is the major challenge, that how we can adopt the quantum mechanics in the real life phenomena. But then, thanks to these three gentlemen who came with a solution, so-called development of multi-scale models for complex system, and for that they won the Nobel Prize in 2013. So they are Martin Karplus, Michael Levitt, and Eria Warshel for the so-called development of hybrid approach, where the mainframe of the system will be described using quantum mechanics, and the remainder of the system will be described using molecular mechanics. So let's see what this method is all about. And in order to explain it, I took this figure from Nobel Prize website, which is of Sir Alfred Nobel. So now you can see that the picture is basically divided into several layers. The innermost layer is highly resoluted, and you can clearly see the eyes, nose, beard, and everything in shape. So this is the smaller region or the reaction center, which require high computational power, and that we can actually assign using the quantum mechanics. So basically, instead of describing the full system, we are only describing the reaction center using the quantum mechanics. The next to it is the interface between the quantum mechanics and the outer region. So here you can see the picture is bit resoluted. You can although see some boundary of coat and tie and shirt, but you cannot pinpoint the exact boundary. So this is how you can describe the system, but with limited information. And third, you have a layer which is fully blurred, so you cannot realize what it is, but it is just a layer of separation. So with this separating layer, we can basically adopt the QM region at the inner core and the molecular mechanics region to describe the whole system, with which we are basically using the approach to solve the experimental spectra. All right. So there are some, schematic representation. Say, for example, when we have the experimental or the model structures in the black, the energetics of the or the potential energy surface will be something looking like this. When we apply the molecular mechanics, it will be going to the immediate local minima. And so you can see the energetics is reduced a little bit. But when we apply the hybrid quantum mechanics and molecular mechanics, the energetics will be further reduced. And so we can say the system energy is more stable and it is more accurate. Now, imagine the same system, how you will describe the spectroscopic phenomena. So if we talk about the ground state of a material, and then the GS stands for the ground state, and then when we excite it, it will go to the excited state. So the energetic gap between the minima of the ground state to that of the excited state is basically the absorbance. So this is what you generally obtain from the UV visible spectra. And then as soon as the molecule moves to the excited state, it will roll down to the minima of the excited state. From there, when it dissipates the energy and comes to the ground state, this is the phenomena which you observe in the fluorescence. So now you can estimate the experimental one, where you get the absorbance and the fluorescence phenomena. It can be described using computational modeling. Uh, in particular, when we model the ground state and the excited state electronic properties. All right. And now we will see one example of how this phenomena can be modeled for the material system. So I want to audience, in case if they have any questions so far for the fundamental aspects of quantum mechanics and the molecular mechanics. So I will be happy to answer in between. Yeah, maybe you can use the microphone, or you can type in case you have any question. Yeah, among the audience, if anybody have any question regarding the methodological aspects, feel free to ask. Yeah, all right. So if I also talk about some softwares with which you can run the molecular mechanics or the MD simulations. So some of them are Amber, which is now freely available for all the academic people, especially when you subscribe them using your academic email ID, you can get Amber for free. The next one is from Schrodinger software, which is called Desmond. So you can also get it free from DE Shaw website. And the difference between the two is one where you can use the Amber-based molecular mechanics force fields, and in another Desmond you can get OPLS-based molecular mechanics force fields. So these are two tools which are freely available for running the classical simulation. The other part is for the quantum mechanics. You can get free programs, say for example, Orca, which is one of the highly used quantum chemistry package. The another one is GEMIS. And if you talk about the free servers, it is say for MD simulation, you can get MD Web, which is freely available, and you can run up to say 500 nanoseconds there. Even though if you do not have any computational resources with you. Likewise, for the quantum chemistry or the DFT thing, you can use Kemp Compute, which is also a free software, and you can access it using the academic email IDs. Yeah. So with which now we will move to the later part where we will see one example of materials in order to model it using the computational tools. So this part of the story will be based on graphene oxide and its functional variants, where we will be quantifying the experimental inferences using the computational modeling. So the story begins. The story linked with the carbonaceous material, that is graphene. So it's hold a very good historic story, that is about Andrew Graham and Konstantin Novoselov when they used to work together in a laboratory. However, among the week work, they also used to do some side projects, especially during the weekends. So this is one of the outcome which they did in the Friday night experiments. So they keep working on graphene, and one fine day they realize that the graphene layers can be separated using a sticky tape, and the tape will contain a very thin layer, but it is still having high mechanical strength, good optical property, and the thermal and conductive property. And later on, they realized that this is the graphene layer, which can be separated using this simplified method. One fine day when the method of preparation for the graphene flakes was discovered, it became soon very popular, and then people started speculating a lot of things. Say, for example, with the graphene, they can build very high mechanical strength structures, and even the ladder from Earth to Moon is possible. But then still we are working on different aspects of graphene in order to fine tune it and to obtain the desirable properties. So this is still an ongoing story, but then graphene came out as a valuable candidate for different purposes, including the biomedical application, where it ranges from drug delivery to tissue engineering and biosensor designing. Now, our concern was to tune it for desirable property and to attain the biocompatibility. First of all, because carbon is one of the abundant element, and so it is also compatible with the biological system. And second, when we do the functionalization of carbon of these carbonaceous material, chances of bioincompatibility will be less. So also we worked on several synthesis and functionalization part where the trivial method of Hummers and modified methods, they has been synthesized, and in addition to this, with the variation in synthetic method, we were able to produce some functional variants. So now in one of the story we will be talking about cysteine, that is an amino acid, and L form is because this is the most common form which is available, which is uh, linked with the biological system. So cysteine contain one of the crucial group, which is thiol, that is SH, and because of which it can be used several times as a reducing agent or the stabilizing agent for the nanoparticles. Now, because cysteine citrate is quite common to use, say, for example, stabilizing the gold nanoparticles, we believe like why not to use this in conjunction with one of the common material. And so we thought to covalently bond it with the graphene material. So this is the typical example of pristine graphene, where you see only the carbon and hydrogen associated with it. And with the method of synthesis of graphene oxide, you introduce a lot of oxygen-based groups. Say, for example, on the corner terminals, we have COH group, and on the edges, we have OH group. And in between, we also have some epoxy group. Now, the introduction of these functional groups will, number one, give rise to different level of degree of oxidation. Number two, if you see, this is a honeycomb kind of lattice, which is highly conjugated, and we have sp3 hybridization. But then we also get sp2 hybridization because of introduction of these oxygen-based materials. Now, when we covalently link the cysteine, it will be linked in two forms. Number one, where the thiol group will be free, and so it can interact with, say, any nanoparticles. And number two, where the thiol group itself will be covalently linked to the graphene oxide. So, in short, the thiol group will not be free to interact with any other external environment. However, the COH group remains the same. And the later possibility is also there, because in the protein environment, we see when two cysteine comes closer, they make disulfide bonds. So this is also possible. Yeah. Sorry. Yeah, so this is also possible when we put the two systems together. Either they will be stacking on top of each other, or they may form a hydrogen. They may form a disulfide bond. So these are some of the possibilities which are possibilities of synthesis when we have the system within our test tube. Now, in order to quantify them, we then did an experiment called dynamic light scattering, where we get the scattering information of light, and then we can quantify the particle size distribution. So you can see that this is the DLS peak for the pristine graphene, and we see one sharp peak here, which describes that the solution contained in the pristine graphene is quite homogeneous. And so is with the graphene oxide, although the graphene oxide size is a bit reduced compared to that of the pristine one. However, after the functionalization of the cysteine with the graphene oxide, we took multiple readings, and in all of them, we see a heterogeneous distribution of the particle size, where we see multiple peaks. And this gives us the hypothesis that what could be the reason? Because when we overlay with the pristine and the graphene oxide, we see that some of the peaks are overlapping, but then there are few new peaks as well. Now, this is the part where we have a material in hand, and we have some experimental observations, and now we want to assign these spectra using the computational modeling. So in order to do so, we run some simulations, and after the simulations, we analyze the thing. And this is one of the common statistical or quantifiable tool that is called the root mean square deviation. So before going into the results, let's discuss how this RMSD information is being obtained. So this is the typical formula of RMSD, where we use this flow. For example, we find the differences or the deviation between two atoms, we square the differences, then we sum up, and then we divide the total data points. So as I described, this is between two atoms. So likewise, we do it for all the atoms present within the system. Then we divide it by the total data point, and finally we do the square root of the result. So in short, when we do this for the entire system, we get the RMSD. But then in the computational modeling, we put the atoms in the spatial location of X, Y, and Z coordinates. So in principle, we can also deconvolute the same in the X, Y, and Z axis, and then we apply the same in order to get the RMSD. However, this part will be done by the algorithm itself, and we are getting the sense out of which is called the chemical intuitions. All right. So now let's talk about the inference that is being achieved using our simulation methods. So this was the cysteine again, and these are the two systems for which we get distinct DLS peaks. Now the RMSD for the pristine one shows it was very uniform across 1 microsecond simulation, and it doesn't show much of the fluctuations. However, when we simulated the graphene oxide, because of the structural defects induced, we see some bending and some butterfly kind of conformation. And so we get two different conformations, which are shown with two different colors. Likewise, when we also see the system, which is where the cysteine is covalently bound, we see that in one of the system where the thiol group is free, there is even higher level of conformational variability, especially when the SH group is free and the COH group is free to interact with the water. And with the other part where the cysteine thiol is linked with the graphene itself, we see further higher level of degree. And we attributed this higher level of conformational variability is because of absence of thiol here. Because then the orientation with the water molecules will be much random. However, in presence of SH, there will be some sort of hydrogen bonding because of which the conformational variability will be restricted. And because COH group is common in both, so we ruled the probability of it. And here we can see now there will be two distinct conformations. Later on, we also have two other models where we either stack it or we have a disulfide bond. So in this case, we see when we stacked the two system containing the cysteine, we see the conformational variability is in a significant way. However, because of the disulfide bond, it is again coming as a flat and a single conformational state, which in turn is somewhat overlapping to that of the pristine. Now, this is quite interesting because as soon as we introduce this single bond between the two structures, we get the RMSD to be a flat line. However, in absence of it, it shows two significant conformational variations. So this could be, the answer why the DLS is giving us multiple peaks. And later on, we further looked into the free energy landscape. Yeah, and we looked into the free energy landscape, where on one axis put the RMSD of the pristine graphene as common, and on another axis we put the other systems as the variables. So you can see that with the pristine and the graphene oxide, we get only one minima. However, with the pristine graphene and cysteine in another model, we see two distinct minima, but the separation between them, the conformational landscape, is little. On the other hand, when the sulfur is attached to the graphene oxide itself, the degree of separation between the two conformations were quite high. And again, when we have the two conformations stacked on top of each other, we see two different conformations, but the separation is not so well. But with the case of say disulfides, again it is giving the same kind of conformation, which is similar to that of the pristine one. So this suggests that when we because in the system, because in the experimental system we do not have a clear demarcation whether this cysteine is attached with a free thiol or linked thiol, or probably there is a stacking phenomena or there is a disulfide phenomena, and so we get multiple peaks. But then the peak was overlapping, for example, with the pristine graphene, and that might correspond to that of the disulfide bond. Likewise, the peak which is overlapping with that of the graphene oxide terms, it might be because of presence of these structures. So in a nutshell, when we try to look at the conformational variability of say pristine graphene and the graphene oxide, graphene oxide and the graphene oxide with two different type of cysteine arrangements, we do not see much more variation except the butterfly kind of structures that is above and below the plane. However, when we see the stacked system without the disulfide bond and with the disulfide bond, we see significant structural conformational deviations and a limited conformational deviation in case of disulfide bond. So this basically confirms our hypothesis of obtaining the DLS spectra, where we see the overlapping peak of pristine graphene. That's because the minima of the disulfide is same to that. And the conformational variation which was there with the graphene oxide and it overlaps because some of the two structures which is present, they are overlapping with them. That is not very high level of separation between them. And to those which are distinct, they might correspond to the stacked system. So with this, we see one example where the computational modeling is helpful in assigning the experimental spectra. And this is the final one where we see the water adsorption, because on the structural defects, the water molecules get adsorbed differentially. So this is one of the examples. Say, for example, you have a material or the graphene system itself without any structural defect. You see the adsorption of water in a different way. As soon as you introduce some of the hybridization change and structural defects, you see the arrangement of the water molecules in a different manner. Likewise, as you increase the structural defects, the arrangement of the solvent molecules will be different, and so is here. And in the similar way, we see some distinct differences in our system. When we have the pristine, we have a different way of water adsorption. And as soon as we introduce some oxygen group, the water adsorption or the near shell of the solvation varies a lot. But in case of cysteine with geo, either side of the attachment where the thiol group is free or the thiol group is linked, there is no differences at all. And in case of say cysteine geo with a dimer, we see the hydration cell is quite distinct in case where the disulfide is introduced. And this pattern of disulfide is quite similar to that of the pristine graphene. And this is the answer how we get from the modeling that what is happening within our test tube system.